Welcome to Season 4 of Science in Parallel, a podcast about people and projects in computational science. I'm your host, Sarah Webb, and this season I'll be talking with guests about creativity, how it fuels both their computational research and their daily lives. We'll start off with an episode about climate modeling and my conversation with Emily de Jong and Tapio Schneider, who are both at the California Institute of Technology, or Caltech. Emily is a graduate student in mechanical engineering, and Tapio is a professor of environmental science and engineering, and he's Emily's PhD advisor. Emily's research is supported by a Department of Energy Computational Science Graduate Fellowship. I spoke with Tapio and Emily in July at that program's annual meeting in Washington, D.C., where Tapio gave a keynote talk about the Climate Modeling Alliance and their work to build a new, more accurate Earth system model that can simulate uncertain processes, such as those within clouds. In this conversation, Emily and Tapio describe how both the science and societal impact of climate modeling motivate them, how outdoor activities and music shape their perspectives, and how they view creativity both inside and outside the lab. Later in the episode, Tapio shares his experience as a science advisor to the Climate Music Project, an artist collaboration that's producing music and video pieces that explore climate change and solutions to the climate crisis. We'll lead into our conversation with one of the pieces that Tapio consulted on, a violin concerto by Theodore Whiprud. This computer-generated clip comes from a section of the piece looking at potentially virtuous changes that could address the crisis. To start, I want to get some context for your interest in climate, how climate change got on each of your radars, and how that became a problem that you decided that you wanted to work on.
I came into climate science after doing some internships in the oil industry. Sort of by accident, when I came to Caltech, I intended to work in some sort of modeling of fluids that was relevant to energy and the environment. And I have had the privilege of meeting Tapio during that first year at Caltech, and it seemed like a really unique opportunity to work on Earth system modeling directly, and specifically this question of aerosols and cloud particles in the atmosphere, which was not a field of science that I had been exposed to prior to coming. I started in chemical engineering, applied to mechanical engineering at Caltech, and found myself working in environmental science and engineering. So it was all sort of an opportunistic set of choices that got me there. But it seemed like an opportunity that I couldn't and shouldn't pass up.
What about you, Tapio?
There's maybe two stories. One is sort of the scientific story you put in a CV, and then there's the life story. I think the scientific story is that my background is in physics and math. I always loved physics of everyday life. And when I started out in physics, that's what I loved learning. Why is the sky blue? And say the quantum mechanics changed all our lives, gave us all these electronics we have. Physics were at the cutting edge when I was a student in the 90s. It was either at absolute zero temperatures or at very high energies. And I was looking for physics at the energy of sunlight, day-to-day life. And so I scientifically thought, climate, atmosphere, oceans is an interesting area to study. I was an exchange student at the University of Washington, has a very good atmospheric science department, oceanography department, where I got to know some people and got to know the field a bit. I applied to grad school in the climate sciences. Not quite knowing, I think, what I was getting into at that point. It appealed that it was a young field where I felt as a young scientist, same is true for Emily now, you can make a contribution that lasts. And, I stayed evidently. It mattered to me, too, that it's an area of human concern. I was concerned about climate change at the time. I used to be a competitive cross-country skier, and ski races kept being postponed and moved, and I started to wonder why that was and became interested in global warming, climate change as a high school student, so it was in the 80s, and that was a factor as well, but maybe not the only factor of how I got to the climate sciences.
Can I just say, it's been a very happy realization of what Tapio mentioned, that it is a young field and that you can make contributions as a scientist in the field. And it's also a very supportive field, which I did not know going into it. But I think that the earth sciences have been especially friendly and welcoming, even to somebody without that background inherently, even compared with fields like more traditional fluid mechanics.
Yeah. It's very much an immigrant field, immigrants from other scientific disciplines. Most of us have a history coming somewhere from the sidelines. It's very open to new people coming in.
And I assume part of that is the interdisciplinarity of it. There's so much information and so much science that goes into understanding climate, right? Can you talk about how you started thinking about what you could bring to the field?
I came into the field thinking, okay, this isn't too different from what I intended to study. It's still particles in some sort of fluid flow. And that's not so different from studying contaminants in groundwater or solid particles in combustion, for instance. So the physics regime is different, but the underlying physics are similar. But there's a lot of terminology in the earth sciences that I had to get familiar with, to the extent that I created my own dictionary of acronyms and words that I kept having to refer back to in my first year, because I had never heard of this liquid water path or ice water path or any of these things that are specific to discussing fluids on a rotating plane, for instance.
Yeah, I think the acronyms can be really a hindrance to entrance. I remember sitting in one of my first atmospheric science seminars at the University of Washington and hearing someone talk about SST for a long time without knowing what this person was talking about, which is sea surface temperature. And over time you assimilate and you learn. I think what makes the field appealing to me is I always liked physics of complex systems and complex systems where many different things come together. I think that was always my physics. More is different, a famous title of an essay. And bringing together ideas from different disciplines, math and physics and computing, I think it's always the kind of science that appealed to me and still does. I think what I still enjoy about the field is how much I still learn every day because the system is so complex. The land biosphere is one example. Didn't know very much before about, and I continue to learn. It's just really fun to bring these ideas together toward a better understanding of how this very complex system operates.
Related to the complexity, I want to ask you each about computing. It's the chicken egg question. Which came first, the climate or the computing?
Computing was definitely first for me. So I grew up in the age of home computers becoming available in the 80s, and I had one of those and was absolutely fascinated by what you can do with computers. In fact, I sold my first software packages when I was 14 or so, participated in computer science competitions as a teenager and the likes. I was very immersed in the computing world. I had a research assistantship as an undergraduate in a biophysics group and building software for a biophysics lab that introduced me to what at the time was higher performance computing. It's, of course, laughably non-performant compared with what we have now. It's the computers we had were less powerful than the watches most people have on their wrists now. But it introduced me, for example, also to the first generation of neural networks at the time. And climate came later, and I worked more on the theory side in climate for a while. But what I do now is very much bringing the computing back strongly, and I like that as well.
Emily, what about you?
Computing also came first for me, in part because the computer science department has such a huge presence at my undergraduate institution, Princeton. I think it's the largest or one of the largest departments by far. So when I got there, I thought, yeah, I'll take some computer science. And I liked it well enough, not well enough to make it my major. And my first research project as an undergraduate, I really dove off the deep end. I reached out to Professor Emily Carter at Princeton. And people in molecular dynamics, very far from what I do now, might be familiar with her. So all of a sudden, I was thrust into this world of learning how to use the terminal, learning how to run and aggregate data on a high-performance computing system. And I would say I have retained those skills. The skills of orbital-free density functional theory have long since escaped me. But that was definitely my first exposure to high-performance computing. And since then, I've always been interested in more of the theory that goes into how you actually design systems of physical equations to function on those HPC processes.
Let's talk about this big challenge of climate. And Tapio, can you talk about when you entered the field of climate, where we were, and how you've approached your career and the kind of challenges that you decided to take on along the way?
As I mentioned, I was working more on a theoretical science in climate, but theory is not just paper and pencil. In our case, theory always means that you use simulations as experiments. The atmospheric sciences are really the first computational science where we use computer experiments in lieu of the actual experiments we would all love to do, but it's hard to build in Earth at lab scale. Basically can't be done to reduce all the processes you want to capture to something you can build in a laboratory. So instead we use simulations. The simulations I used were atmospheric, it's called general circulation models, so global atmosphere models that were simplifying things like precipitation and cloud processes. And I used them to study properties of atmospheric turbulence, what's called the macroturbulence, or large-scale turbulence driven by the gradient in solar heating between equator and the pole. I used computers primarily to generate large numbers of experiments with which I could test theories, from which I could develop theories, and was doing things like what you would do as an experimental scientist, vary parameters over wide ranges like Earth's rotation rate, the size of the planet, insolation properties, and often vary them wildly beyond anything that has occurred on Earth or even on other planets potentially, to elucidate fundamental properties of turbulence. That's how I used computing. I was very much a user of models at the time, and that I took, in that case, a model from GFDL and NOAA Lab in Princeton, where I was doing my grad school, and stripped it down to the experimental device that I wanted to work on. But I wasn't developing the model myself. So that's something that came more recently, that climate models are imperfect is not a new realization, but maybe a decade or so, I thought in academic circles, people often lament that climate models are not as good as they could be, but we should do something about it. We have academic freedom. We can work on essentially whatever we like. And the biggest problem in climate prediction are small scale processes, for example, like control clouds. So I decided to work on those types of processes. Before I was working on turbulence in thousands of kilometer scales, and then started to work on scales of meters to kilometers or so. And first, again, to understand properties of these small-scale dynamics, but now also to build new models that capture those small-scale dynamics better. So now with Emily and many others in a group, we're actually building all new software, all new models ourselves.
So, Emily, it sounds like these kinds of physical questions were things you were interested in. As you've been thinking about this as a graduate student, what problems have you grabbed onto? What are you most excited about tackling?
So when I first came to Tapio and expressed an interest in working in his group, he asked what kind of problems I like to work on. And I said, I like building things. I like building models and thinking about the math that goes into them. So I was almost more motivated by that sort of hands-on application than by the fundamental science questions themselves, in part because I didn't know what they were in this field. And so the question that I eventually latched onto is one about cloud microphysics, which if you ask many people in the climate sciences, it's something that they wouldn't touch with a 10-foot pole because it's messy and difficult and problematic. In fact, somebody said exactly that to me at a climate dynamics workshop in Norway last year. They were glad somebody else was working on it. And there's a lot of complexity that goes into cloud microphysics. It's all of these droplets in the atmosphere that we can't directly resolve or model. And yet, somehow we need to understand what's going on with them if we want to understand how clouds will respond to global warming, how changes in aerosol concentration change the clouds, and that feeds back onto the planet, for instance. And I found myself diving very, very deep into one question about cloud microphysics, which is, when do cloud droplets become rain droplets? And if you think about it logically, it has a very simple answer. It's at the moment that they fall out of the sky. But that's not necessarily what the models themselves are keeping track of. And this is sort of one of the canonical and long unsolved problems in cloud microphysics, because it's something where we have to create artificial parameterizations. And that introduces a lot of uncertainty into these models. So the problem I've taken a deep dive on in quite a bit of my research now is this question of how we can keep track of cloud droplets or rain droplets, for instance, all these hydrometeors in the sky, keep track of their size, keep track of how they interact, how they collide and coalesce with each other, and how that leads to then precipitation. And that requires thinking a little bit more creatively about what quantities we actually keep track of in our climate systems or in our large eddy or weather models in order to accurately model those physics.
I think we're in a very interesting space with any computational science field where you would love to have computers that could do more than they do. I want to get a sense from each of you about the interplay between computers and science and how the power of the computer drives the question that you're able to answer and how you think about how to make progress when you're working at the edge of what your tools can do.
Well, I think it's pretty clear with cloud microphysics that limitations in computational ability are the reason that I am able to study what I do. If we had infinite computing power, we would resolve individual cloud droplets in maybe a Monte Carlo simulation, for instance, and we would have, 10 to the fifth droplets per, cubic centimeter. That's obviously infeasible. And so that is sort of the driving force, the fact that we don't have that kind of computational power and won't for the foreseeable future is the reason why we have to come up with approximations of the physics that take place between cloud droplets. Not because we don't understand them at all, but because our understanding cannot be realistically modeled on existing computational platforms. So that then drives the question in mathematics, in parametric and structural uncertainties of the model, also in observations, in trying to come up with data to actually learn and reduce some of those uncertainties from.
Yeah, I like that perspective that because of finite computational capacity, scientists will remain necessary for a long time in this field. I agree. I think the role of computing has always been large in the climate sciences. In fact, John von Neumann, who designed the modern computer architecture at the Institute for Advanced Study in Princeton at the time, realized right after the Second World War that the atmosphere is an interesting computational challenge. And so the ENIAC, the first computer first used for artillery calculations, the first scientific problems it was used for was weather prediction, atmospheric simulations. John von Neumann started a weather prediction effort, hired a number of, at the time, young people who in some ways became the founders of the modern atmospheric sciences, Jules Charney and Norm Phillips. And so the atmospheric sciences are the first computational science. It's 1947. People used computers to study the atmosphere numerically. And the climate sciences have always been at the forefront of computing, using the biggest computers available at any given time. Whatever DOE is building, climate simulations are being run on it. And the reason is what Emily said, that in principle, it would be nice if you could resolve more. But there is just such a vast range of scales, it's completely infeasible. So the atmospheric turbulence alone has 10 to the 27 spatial degrees of freedom. No way to retain that in memory. And that's just the turbulence. That's not even covering what Emily talked about, the microphysics that happens on yet smaller scales. So the biggest computers we can get will fill up, and it will not be enough to simulate everything that matters, down from cloud droplets, aerosols, to planetary scale circulations. And hence, scientists, engineers who augment the powers of computers will remain essential.
What are your passions and interests outside of science? How does that help fuel you when you are focusing on the problems at hand?
These days, I spend a lot of time in the outdoors, and I feel very grateful that Tapio is an advisor who encourages and supports that, especially after moving to California, where the weather is somehow much better than that of New Jersey, believe it or not. I found myself spending a lot of time outside with my original hobby of cycling and also taking up new things like rock climbing and mountaineering. And I definitely now have the opportunity to think about what's going on in the atmosphere and in clouds in particular when I'm out there. I don't want to say that that's 100% what I'm doing out in the field. I like to describe my bike rides as observational field work, but that's truthfully not actually the goal of them. But there's something really fascinating about waking up early in the morning, bicycling up a small mountain outside of Pasadena, and all of a sudden emerging on top of this stratocumulus layer. So you're looking out and you see just a layer of clouds as far as the eye can see, and actually having some understanding of what's going on there, why that happens, what's going to happen to that cloud as the day goes on, that otherwise I might have been completely unaware of, maybe just seeing the cloud as like an impediment to my visibility of the ocean or other things or something inconvenient. And so it's definitely changed my perspective a little bit. It's even more important if I think about going on like a big mountaineering expedition, for instance, and thinking about how important weather is for the success of climbing a big mountain. That's something that I used to think of as, oh, it's a completely random phenomenon. It just happens and you get lucky or you don't. But it almost gives me a greater sense of control to have an understanding of what's going on and why, even if it doesn't actually help me get off the mountain any more safely in the end.
Safety is important. As I mentioned, I used to be a competitive cross-country skier, and it's still my favorite form of locomotion. So whenever I can, I try to get on cross-country skis or sometimes roller skis. And I have children, they're 11 and 13, so that's obviously a large part of my life. They are all very active, love being outdoors too, so this is something we all do together. One of my sons especially is a very avid snowboarder, and the other skis. I did get into the field in part because of disappearing snow where I grew up. That's actually quite striking. We used to have something like 120 days of snow on the ground per year, and it's reduced by almost a factor 2 by now, and it's clear that soon there won't be any.
You're working on one of the grand challenges for the world right now. How does that affect you? It can affect your work.
It lends a lot of urgency to the work. So I think in a lot of science problems, I think, well, you have your career, and whether you figure it out this year or in 5 years, it doesn't matter that much. So here it really matters. We really want rapid progress because we need the information for all sorts of adaptation decisions, infrastructure planning decisions, and the like. So it puts more time pressure on what we do than you usually have in science. It means that the scientific information we provide, the value of that scientific information is in some ways a decreasing function of time. At some point, the climate system will have shown us how it will change, and we want to predict that, not know it after the fact. So I think it is very motivating. At the same time, we're scientists, engineers. I think I am, and I think most others in the group are also very much motivated by these scientific problems in themselves because they're just very interesting apart from the urgency of solving them. And again, that's just working on complex problems, intriguing phenomena emerging on macro scales from equations we can write down on micro scales. And by looking at the equations, you wouldn't be able to tell what beautiful things appear on the large scales. And I think that to me is also a motivating factor. But obviously right now, there is the practical motivation. And what I love about what we do is that it seems to be this perfect marriage of fundamental science and engineering, interesting problems with immediate applications and immediate societal needs for planning and the like. And communication is always an important part of science and engineering. You want people to use what you do, and so that's always important. Of course, in our case, perhaps even more important because more people pay attention. And the public debate on global warming, I've been following that now for more than 30 years and have been part of it to some extent. I would like our science to be a bit above the day-to-day of that. And while I'm happy to advise decision makers, for example, on scientific questions, it's a long view I take in that work as well.
Emily is somebody who's your early career. What has that been like for you coming in? Because coming into this field at a different discussion of climate change, I mean, we are seeing the impacts of it in very real ways. People talk about it in a different way than they did 20, 25 years ago. So what does that mean for you?
It's interesting you say people talk about it differently because I grew up outside of Fort Worth, Texas, where I think maybe the discussion on climate change is 10 years behind where it might be elsewhere in the United States. Maybe partly as a result of that, it wasn't something that was high on my radar in terms of actual understanding of the fundamental questions and problems, other than knowing that it was a hot and controversial topic, until I was maybe partway through college, actually. And so for me, the fundamental question was always this question of energy availability and security. And that was in part motivated by an inherent understanding that that will need to change, partly as a result of global warming. So that was one of the underlying motivations, but the question I always found interesting, especially in college, was where are we going to get our energy from as people continue to demand more and more of it, both in the United States and also elsewhere in the world? And so that was initially what motivated some of my research, both in the oil industry and also at Princeton as an undergraduate. And when I came to Caltech, that was also part of my inherent motivation. And so it was completely new for me to be able to think about the questions, well, what actually causes these changes under global warming or under CO2 or aerosol emissions in particular that lead to these upcoming challenges? And so in some ways, I actually feel empowered now in thinking about these questions, empowered by having a more clear understanding of what those changes may or may not look like. And I don't know, that feels good. It feels much better to feel empowered to solve problems than it does to feel like the work that I do leads to negative conclusions or negative outcomes for the planet. And I think it's also much easier to talk to people, especially people where I'm from, for instance, in terms of solutions and specific challenges, as opposed to what is seen as a controversial national topic.
That's the thing that has most changed over my career in this field, that now you can talk about solutions and they're on the horizon. You can see what a solution looks like. When I started working in the field and started worrying about global warming, there was no clear solution. I mean, the problem, I would say, was to me just as acute in the 90s as it is now. The big picture predictions haven't changed dramatically, so it was foreseeable what will happen, and it has happened now. But in the 1990s, it was difficult to see how we solve this. I was grad school. I wasn't flying to conferences, was taking trains and buses all over the US and such things, but that was not a scalable solution to the problem. And what's really interesting now is that solar power has gotten so much cheaper, dropped by almost a factor 10 in the last 10 plus years in cost. Renewable technologies have become cost competitive with fossil fuels, and in fact are cheaper than fossil fuels for new installations in many places. That a solution seems to be on the horizon. There's no easy solution. These are still hard problems, and there are still many engineering, regulatory, legislative issues to be solved. But one can see how it can be done now, and that was harder 30 years ago.
So Tapio, I wanted to ask you a bit about the climate music project. How do you illustrate to people what is going on in this very complex system that is our home on our planet?
The Climate Music Project is a project that pairs musicians, composers, songwriters, and the like with climate scientists to create music that addresses global warming and to some degree solutions as well. I feel it is important also to make clear this is not all doom and gloom. There is a way out. And the Climate Music Project to me has just been a source of joy and fun. I mean,
how did that get started?
The people came to me in that case who had started the project. And then we've had, for example, there's an ongoing project with a composer writing a concerto that thematizes global warming. We had sessions with songwriters. It's just not the thing that we have in our day-to-day working life. And Emily and I meet, no one breaks out the guitar and breaks out into song. And so here we were sitting with a bunch of songwriters and he give us an idea for a song, and they take out the guitar and say, how about this? And
I want to be cool, it isn't a joke to walk in the woods without all the smoke. I love to swim, but not in a flood. We can't grow a crop down in the mud.
Coming up with lyrics together. And that's just really enjoyable, and also enjoyable to see how what these talented musicians make out of it can connect with people on a very different level.
How much do you learn about how people connect with it? Are there concerts or do you get feedback in some way?
Yeah, there are concerts. There are records released now by these songwriters whom we're working. I think some coming out soon. And yeah.
It's really awesome. It sounds like you play a little bit.
I used to play clarinet primarily and saxophone, and mostly high school and a bit beyond. I always thought of myself as a poor musician. It turns out I was playing with people who all became professional musicians, so they were very good, and then relatively I was not very good. But yeah, I don't play much anymore myself.
Tapio, do you have any bassoonists on your roster of climate musicians these days?
People directly working with, no, but there are orchestral pieces, including bassoons. So if you're interested, yeah, maybe there's a concerto that you can get involved in one day.
That'd be very cool.
Yeah.
So you're a bassoonist then, Emily?
Yeah, I would say until I moved to California and got the outdoor bug, I was very focused on music as a kid, through high school, even in college. It took a back seat a little bit, in part because I was burnt out from it when I got to Caltech, and rock climbing was infinitely more interesting at the time. I was actually not super familiar with Tapio's climate and music project, but I think he has an excellent point that music can express and communicate inherent emotions and aspects of being human that it's very easy to turn your ears off to when listening to somebody speak at you or try to communicate through words. And it's been some time since I was able to really appreciate that aspect of music. And so I'll be really interested to hear these albums when they come out.
Yeah.
This is a really open-ended question, but I hope you're willing to play. For each of you, as scientists, as humans on the Earth, what does creativity mean to you?
I think to me, the main creative outlet is just the scientific work we're doing. I mean, to me, producing a good model that is excellent software, conceptually first in class, that is creativity. And this is, I think, my main creative outlet is that work. In the age of big data, there is a latent fear sometimes expressed about loss of creativity for a scientist. We're all going to be replaced by a black box machine learning model that just learns all the science from the data out there in the world. And I think that fear is overblown. I think scientific engineering creativity will remain absolutely essential for progress in this field for several reasons. But one really simple one is that the degrees of freedom in the climate system is just so vast, from cloud microphysics to planetary circulations to plants and the rest. There is, I think, no way to learn all of that from data. We have a lot of data, but not enough to learn all of that directly. There is an important role still for scientific creativity that in the end is augmented with data, human creativity. I think the way we achieve progress and the most rapid progress is by combining human creativity and, say, providing structure for physical models and the like with learning from data to allow us to make more rapid progress than the field has made over the past few decades.
I feel like creativity can play into work and research, but also into any sort of activity you do in life. And it's where you pull a tool out of the tool belt that's not built for the thing you're trying to hammer, and somehow it works anyways. So, for instance, in modeling cloud microphysics, that could be pulling a numerical tool that hasn't been applied to cloud microphysics and trying to finagle it to work. In music, it's putting together sounds and harmonies that communicate some sort of emotion for reasons we don't really understand. Even in the outdoors, for instance, one of my favorite things is just sort of MacGyvering, whether it's in my backyard or if I'm 100 feet up on a climbing wall and figure out some sort of random rope system to, pull up a water bottle because I just decided right in that moment that I need a sip of water from the person who's 100 feet below me, building a rope swing off of a canyon wall. Just that kind of fun sort of creativity is also something that I enjoy a lot.
Is there anything that we haven't talked about that you think is important to mention about either the field of climate modeling, where we're headed, basically? What have we missed?
I think it's worth just re-emphasizing this idea that you don't need to be a classically trained climate scientist to play in that sphere. Tapio and I mentioned this earlier, that a lot of people come into it from different backgrounds, and yet I imagine that from the outside it can still look like an intimidating field, particularly if you don't understand the jargon or feel insecure in your knowledge of Earth systems. But I feel like that's partly where a lot of the ingenuity and creativity can come from, is from people who haven't yet been exposed to the somewhat narrow set of computational tools that have been and are currently being applied to modeling the climate system. And bringing tools and ideas from other fields, I think, is a way that innovation hopefully can continue to happen in that field of climate science.
With that, I'm going to wrap up. Thank you, Tapio. Thank you, Emily. It was such a pleasure talking with you.
Nice talking with you.
Nice.
Thank you, Sarah.
Thank you very much.
To learn more about Tapio Schneider, Emily de Jong, and research and ideas mentioned in this episode, check out our show notes at scienceinparallel.org. We also have links and more information there about the Climate Music Project, related initiatives, and the music and musicians featured in this episode. Special thanks to Stefan Crawford, founder and executive director of the Climate Music Project, and to Theodore Whiprud, Will Kimbrough, and Brant Miller for allowing us to use clips from their work. Science in Parallel is produced by the Krell Institute and is a media project of the Department of Energy Computational Science Graduate Fellowship Program. Any opinions expressed are those of the speaker and not those of their employers, the Krell Institute, or the U.S. Department of Energy. Our theme music is by Steve O'Reilly. This episode was written, produced, and edited by Sarah Webb. We'll play out the episode with a bit more of the song I Want to Be Cool by Will Kimbrough and Brant Miller that was featured earlier. The song is the center of a new climate action campaign called Be Cool, which is a collaboration between the Climate Music Project and Music Declares Emergency.
To say what we got. So every girl and every boy can live a good, long, happy life and find some joy.